So hello and welcome. My name is Raymond. I'm going to talk to you about the formation of planetary systems. And I'm an astronomer at the Laboratoire d'Astrophysique de Bordeaux. And before I get going, I'll mention that some of the slides that I'm going to show you today have been taken from these other researchers too. So, what is planet formation anyway? Right? Planet formation is kind of a big umbrella term that covers a lot of different stuff. Going basically from, the starting point is planet-forming disks, gas-dominated planet-forming disks around young stars, like the one you can see at the top left here, which is an ALMA image of an actual disk. The transition from those types of disks to the planets that we see, our very familiar solar system planets, as well as the thousands of exoplanets that we know right now. And I like to think of planet formation as kind of a puzzle process. So you can see this box of puzzle right there. You can buy a solar system formation puzzle if you want. And so really planet formation is assembling different processes of planet formation into a coherent picture that explains the things that we see. So here's an outline of kind of the parts that we're going to talk about here. So to start off, I'll talk about observational constraints. What is it exactly that planet formation models are trying to explain? Because it's important to know where you're going. The second part will be the stages, based on what we think we know now, the different steps of planet formation, how things grow. Then we'll look in some detail at exoplanet systems and talk about how we think they form. And then we'll wrap up talking about how we think the solar system formed. And I'll just mention a little bit, since this is an astrobiology thing, we'll talk a little bit about the origin of Earth's water, since water is obviously of great importance from an astrobiological standpoint. So here we go, observational constraints. And within observational constraints, I'm even going to chop it down further. We'll start off with a little kind of thought experiment I like to do that I call the solar system in context. Then we'll talk about solar system constraints. Then we'll talk about exoplanet constraints. And then we'll talk about planet-forming disks. Right? And so there's a lot of these constraints, and I'll keep bringing them up again even in the later sections. But it's kind of key to know why we're doing this. And in some sense, these constraints show the breadth of the umbrella of planet formation, showing just how far it extends into other fields. Because planet formation is not just one little field, it really extends over many different subfields of astronomy and planetary science. So here we go. Here's our solar system. You should all be pretty familiar with this, I hope. So we got our 8 planets that we know and love, 4 little puny rocky ones close to the sun, and then some big gas balls further out. So, this is our solar system. Now we can say, well, when we talk about other solar systems, what do we know about them? Well, we know what we know from the detection techniques we have from finding exoplanet systems. And I'm not going to talk about those detection techniques in this talk. They'll come up in a later talk at the school. But we can do a thought experiment. We can say, well, if we were to observe the solar system as an exoplanet system, so say we wanted to use current present-day, exoplanet finding techniques to find an exact replica of the solar system, what would we find? And the answer is, almost certainly, we would find this. We would find Jupiter and nothing else, right? The reason for that is the small planets that we know and love, like Earth, are a little too small and not quite close in enough to actually be found by methods like the transit method or even the radial velocity method. So we can't find the rocky planets. Jupiter would be found by a long-term, decades-long survey of the sun's radial velocity by seeing the sun wobble due to Jupiter's presence with an orbital period of 12 years. And we can get information on Jupiter's mass, we can get information on its orbital period, its orbital size, and its orbital shape. But we couldn't see Saturn or the ice giants because they have a similar effect on the sun, but that effect is too long in time. It takes too long. You have to watch the sun for 30 years to see it wobble due to Saturn, or even longer for the ice giants. And so we wouldn't see them. So all we would see is Jupiter. So the solar system as an exoplanet system is the Sun-Jupiter system for now. Right? As our techniques improve, we'll be able to find the other planets. But for now, this is all we got. And so you could say, well, if this is really what we could see in terms of the exosolar system, how does this fit in a bigger context? And again, I'm kind of jumping ahead here because you'll learn a lot more about exoplanets in other talks. And so I'm kind of jumping ahead a little bit. But here is one way to slice up what we know about exoplanets to put the solar system in this larger context. And so let me guide you through this diagram. So starting from the top, the picture of the sun, looking at sun-like stars, the thickness of the line corresponds to basically the occurrence of different outcomes. So following down that line of 100% of sun-like stars, you can ask the question, well, what fraction of those sun-like stars have Jupiter-like planets? And what do we mean by Jupiter-like? Jupiter's size or Jupiter mass planets. And the answer is about 10%. Okay, so that goes off to the left. All right, so about 90% don't. Well, what do they have? Well, a decent fraction of those have other types of planets, like close-in super-Earths, for example. But only about 10% have Jupiters. Then the next question we can ask is, well, what fraction of those Jupiters have Jupiter-like orbits, meaning very wide, relatively wide and relatively circular orbits like our own Jupiters? And the answer is, again, about 10%. Most Jupiters, or Jupiter mass or Jupiter size planets that we know of, have very non-Jupiter-like orbits. Orbits that are either much closer to their stars or more often are much more stretched out. So they often have orbital radii that are similar to our own Jupiters, or maybe a little smaller, but their orbits are much more stretched out, much more elliptical, much more eccentric than our own Jupiters. Right? So that's the more common Jupiter. But our own Jupiter is, about a 10%. It's not unique. They exist. Jupiter analogs exist, but there's not a ton of them. And so just by this very simple thought experiment, we can already put our solar system in about a 1% minority among sun-like stars, right? Just from what we could actually detect. And this doesn't take into account yet planets that we can't detect yet. So the name of the game here in terms of planet formation is to say, well, we have this kind of picture, this way of slicing up planetary systems where we put our solar system in this bigger context. But how do we explain this from a point of view of how planets grow and evolve, and why do some systems look like they do and others look like the solar system? And that's kind of the goal of this big picture planet formation stuff that goes from protoplanetary disk studies through many different processes. I threw up a bunch of words here that are just words that you'll see throughout the talk, and you may see when you read papers. These are kind of the puzzle pieces, in some sense, of planet formation. And so we're going to go through many of these different pieces as we go. And of course, this also connects to the constraints. And so the constraints that we can measure are things like related to protoplanetary disks, things related to the solar system, to exoplanet populations, and a lot of different things. And a lot of, one key tool that we'll be using are computer simulations, because we would love to actually watch planets form in action. And we think that, when we look at disks around other stars, we may be seeing that in many cases. But it takes so long that we can't wait a million years to see what happens. We got to speed it up a little bit. And that's where computer simulations come in. And so a lot of these processes, the tool that we use to study them is computer simulations. So what are the constraints for our solar system that we're trying to, that we would like to reproduce with a planet formation puzzle or model anyway? So let me go through a few of these, right? The thing about the solar system that's interesting is we know so much about it. And so one kind of philosophical question is to ask, well, if we're building a model to reproduce the solar system, what exactly are we trying to reproduce? Just the 8 planets exactly on their perfect orbits with perfect compositions and every asteroid in the right place? Or some kind of broad smeared out version of that? Or which constraints matter more than others? Do we care more about the asteroid belt or about Mars's orbit or Mars's size? These are the kind of things that must be taken into account when you're actually trying to do this in practice. And so it's useful to kind of go through the different aspects here to think about them. So what do we got? Well, the key thing, we got to get the planets' orbits right. So the planets are in a very thin plane. All of the planets are in the same plane to within a couple degrees. They generally have very low eccentricities. That means their orbits are very circular, but not perfectly circular. And exactly how not perfectly circular matters a lot, it turns out, because the difference between an eccentricity of 5% and an eccentricity of 1% from a dynamics point of view makes a big difference, especially for the giant planets. And it's also important to realize that these planetary orbits are not fixed in time. It's not something that's just, we need to get this kind of set picture and that's how it's going to be. Even in the current day solar system, as you can see, this is the eccentricity of Earth's orbit in time on a time span of several thousand years. And you can see its orbit changes shape in time. And so that's a consequence of other planets kicking on Earth's orbit as it kicks on theirs at the same time. And this has consequences, for example, for the climate on long time scales via the Milankovitch cycles and so on. And so it's just another kind of constraint, another thing to think about. The compositions of the planets matter a lot too, right? We got 4 small rock balls, a couple giant gas balls, and 2 icy gaseous balls further out, right? These things matter. And so what planets are made of reflect what they formed out of within this disk and how that stuff moved around and collided and grew into the planets. And so that's a kind of a key constraint there. The fact that we don't in the solar system have an ice giant right next to the sun is a constraint. There's also the asteroid belt, the leftover junk, right? The asteroid belt, the comets and asteroids are in some sense, you can think of them as the leftovers that were not incorporated into planets. And so that's kind of useful. The stuff that does not end up in the planets can be a useful tracer. You can say, well, maybe the compositions of some asteroids represent something about that, the stuff that was incorporated into the Earth, and that little piece just happened not to be, and so we can study that and learn something about it. Of course, it's a biased sample because it's the leftovers, and from a dynamical point of view, it's not the same stuff that ended up in the planet. But that's all right. So in terms of the asteroid belt itself, the details of the orbital structure and the compositional structure of the belt is another constraint. And so the asteroid belt itself only contains less than 1,000th of an Earth mass in total. So it's relatively empty, it turns out. But the orbits of the asteroids are relatively excited, and the asteroid belt is not just a uniform mix of different stuff. As you can see in this plot, there's many different types of asteroids, and the inner belt is kind of dominated by what we call S-type asteroids, things that are relatively dry. And beyond 2.5 AU or so, the belt is dominated by what we call C-types, things that are relatively volatile rich. Finally, the Kuiper belt, which is kind of the main repository for outer solar system leftover stuff, is another constraint. And I'm not going to talk about it much in what we'll talk about today, but it's good to be aware of. It's analogous to the asteroid belt in terms of having orbital structure that actually tells us something about what the planets were doing, and its overall mass, its overall distribution of compositions, which has some differences also, are definitely telling us something about how the giant planets' orbits evolved as they interacted with this outer disk of leftover stuff. All right, let's move on to exoplanet constraints now. So here is a slightly out of date now, but you get the general idea. Picture of the distribution of known exoplanets. Okay? And the color indicates the detection method. Red ones were found with the transit method. Blue ones were found with the radial velocity technique. And I've included the solar system planets on here just to give you a sense of scale. And so we're seeing, planet size versus orbital distance. And what you can see is, Venus and Earth are way below all the dots. What does that mean? That means they're too small to be found by our current exoplanet finding techniques, right? This is what we were talking about before. Jupiter, you can see Jupiter is kind of right on the edge of this clump of blue dots. What does that mean? Well, that's why I was saying that the solar system in context is just the Jupiter-Sun system. Jupiter is detectable with exoplanet finding techniques, but just barely. That's why it's sort of on the edge of the distribution. Saturn is a little too low in mass and a little too far out to be found. But in terms of what we got now, in terms of all the planets that we have found, there's more than 4,000 of these guys, and they can, you can see 3 distinct clumps here. And so, what are these clumps? All right, the clumps are the one on the top left are the hot Jupiters. These were the first exoplanets that were found, because they're easy to find. They're really big planets, really close to their stars, so they have a very strong influence on their stars, so they're relatively easy to find. Further out are the kind of, quote, normal Jupiters, the wider separation Jupiters, planets that are Jupiter's size or mass that are further from their stars. And our Jupiter is kind of part of that group. And those are found typically with only one technique because it's easier to find them. Then at the bottom, there is this gigantic clump of what we call hot super Earths. And they're also given other names. Sometimes they're called sub-Neptunes if you have a good constraint on just how puffy they are. And this class of planets is very abundant. Something like 1/3 to 1/2 of all main sequence stars have a hot super Earth. And so they're clearly a really important category of planetary system, and one that we don't have in our own solar system. They tend to be planets that are a little bit bigger than Earth, between up to say 3 or 4 times the size of Earth. And that's where the super comes from, just being like slightly bigger than Earth. Although it kind of makes it sound funny, that super part, but I don't know. All right, so this is the kind of the categories of exoplanets that we've got right now. So what do we look like? They look like in terms of their distributions of sizes. Here is a graph of the distribution of the sizes of exoplanets. Basically what fraction of stars have a planet of a given size as a function of that size. Not a lot of stars have really big planets, right? Jupiters are much less common than Neptunes. Neptune is a few times the size of Earth. And you can see this big spike, this big increase in terms of the number of planets that have, that are a little bit bigger than Earth. There's this interesting dip in the middle, this gap between things that are more like Earth size and things that are more like Uranus and Neptune size. And exactly what that means is currently being debated today. It may have to do with a division between what we call super Earths that are kind of big rocky things on the smaller side and more like mini Neptunes on the larger side. It's still not 100% nailed down, but that's the current favored explanation for it. Here is kind of a very simple graph of the occurrence rate of different types of planets around stars, where the color scale really just represents what fraction of stars have a planet within a given box. And so red means more. And so I'm not showing you this so you remember any of the colors or anything, just to show that we have enough planets now to go into a decent amount of detail in terms of what the exoplanet population looks like. And so it's a pretty exciting time in exoplanet studies from that point of view. It's not just, we're not just looking at 3 different cases, we're looking at thousands of different members of this population that can be kind of sliced and diced in different ways. Another constraint that will come up again, and I'll talk about this more later, is the period ratio distribution. And so we'll talk about that more later. I won't go into detail on it now. There's also just the distribution of gas giants. As you could see in that initial plot I showed you, there's a clump of hot Jupiters and a clump of what I call normal Jupiters. And this plot just shows that kind of the distribution of the occurrence rates of Jupiters or giant planets as a function of orbital distance. And so, you got this little clump of hot Jupiters, then there's very few of these warm Jupiters, and then the cool or normal Jupiters are further out. And what you can see is that even though the hot Jupiters were found first and they're the easiest to find, it doesn't mean they're the most common, right? There's actually very few of them out there. Something like, maybe ballpark 1% of Sun-like stars have a hot Jupiter, whereas at least 10% or so have a normal Jupiter. It's just that because of observational bias, the fact that the hot Jupiters are easier to find, we found them first, and they've been studied a lot more in some sense than the cooler normal Jupiters. Here's another key constraint that will come back later, which is the eccentricity distribution of giant exoplanets. And so I included Jupiter on the scale here too. So eccentricity, right, is a measure of just how stretched out a planet's orbit is. And so naively, when thinking about planets around other stars, before any were found, well, the giant planets and all the planets in the solar system have relatively circular orbits. And so people thought, well, planets around other stars should probably have pretty circular orbits too. And that's not the case, right? So this is one of the many surprises of exoplanets. And so what you can see here is, close to the sun at small separation, you see the clump of hot Jupiters. Most of those do have relatively circular orbits. And it's not certain whether that means they formed on circular orbits or whether they at some point had more eccentric orbits and a sort of dissipative process changed the shape of their orbits and made them more circular. The main dissipative process would be tides basically tidal dissipation within the planet and the star. Further out, where tides don't really matter, far from the star, giant planets have very high eccentricities. The median, the typical eccentricity is about 25%. And it goes all the way up to above 90%. And so this very broad eccentricity distribution of giant planets, as I mentioned when we were putting the solar system in context, most giant planets have more stretched out orbits than Jupiter. Not all of them, but a lot of them. This is kind of a key constraint on what must have happened to these systems. And we'll talk about that more as we go. There's some other kind of correlations that are interesting to look at. For example, low mass stars, so stars like M stars that are less massive than the sun, have been shown in multiple studies to actually have more mass and more planets close to them and more mass in these planets. And exactly why is still kind of being debated. It's got to fit in the picture somewhere. And there's some ideas here and there, but no one knows exactly why. It's an interesting, constraint. So there's many more exoplanet constraints I could talk about, but we're going to jump along to protoplanetary disks. What are we trying to constrain here? Well, the cool thing about protoplanetary disks is that we have pictures of them. Right? For years, once the planet's orbits were relatively well known, the fact that they move more or less in a line on the sky tells you that they're more or less in the same plane. And that can make you think that they must have formed within a disk, right? As was proposed by Laplace, maybe? Many people hundreds of years ago proposed that the solar system probably formed in a disk. And now we can see these disks. We have pictures of them, which is awesome. And so these are old pictures from the 90s where the disk itself, as you can see, especially in the top, say in the top couple images, they look kind of like a hamburger. The meat is the disk. It's a dust disk that's blocking the light from the central star. And in some cases, you can even see jets coming out, polar jets along there in the bottom left-hand one. These were spectacular images taken by the Hubble Space Telescope. And now we have even better ones taken by ALMA, which is a radio telescope that looks at wavelengths that are about a millimeter, a little bit less than a millimeter. And so here's two specific examples of disks that were observed with ALMA. And it's cool. You can see all sorts of detail. You can see little rings in there, little lanes, sometimes little clumps, sometimes spiral waves. There's lots of detail that we can see in there now. A very famous survey that was done 3 years ago, I think, with ALMA was a survey of, I think it was 20 disks or so, and just to look at what's out there. If we look with the best resolution that our best telescope has, what do planet-forming disks look like? And here's what they look like in terms of where the dust is, right? This is not sensitive to the gas, it's more the dust. And you can see sometimes some disks have rings, some look relatively smooth, some are different sizes than others, some have other types of structures. There's a lot of variety in terms of what disks, the birthplaces of planets, look like. And maybe that has a key influence on what the planets look like. And so what kind of masses are we dealing with here? It's possible to measure the masses in disks around young stars. It's not the most reliable measurements, but they're a constraint. And so you can see here on the y-axis the estimated mass in a disk as a function of the stellar mass. And so you can see, the first thing you can see is there's a giant scatter. So for stars that are roughly, like the sun, there's a scatter of 2 orders of magnitude in terms of how much stuff is actually inferred to be in the disk, right? That means that some disks might just start off with a lot more stuff than others, meaning they have a lot more stuff to build planets. Around very low mass stars, it seems like there's generally less stuff, and around high mass stars, there's more. Right? Exactly how it scales, we're kind of led to believe that it's a nice linear scaling, but that's not necessarily the case. Current studies show that there's probably like a pretty strong correlation between the mass of stuff in a disk and the amount of mass in the star. So small stars might have less stuff to form planets than big ones, so maybe you would expect more big planets around more massive stars, which is indeed the case. But it's not, connecting all the dots has not really been done. And it's possible that the disk masses that were in those 2 previous plots are not really showing, they may not really be representative of the amount of mass that's available for building planets. And why would I say something like that? Well, it's because if you add up these the lines here, the blue and red lines, are showing if you take exoplanet systems and add up all the mass that's in them, then you can compare it with those gray curves, which is the amount of mass we, from measuring the disks themselves, how much mass we think is there. And in some cases, there's not enough. So especially for the small stars, there's more mass in the planets than we think should even be in the whole disk. And that doesn't make any sense, right? And so maybe the disk masses that are being observed are not really capturing the amount of stuff that was building the planets. Maybe we're seeing them too late in the game and the planets have already formed and so the disk mass is already less. Or maybe somehow something related to the technique of measuring the mass is getting you the wrong number, a number that's too small. It's kind of being debated. But clearly it's not clear what's going on there. And another thing that we can see directly is, well, regardless of exactly how much mass started off in a disk, the amount of mass goes down in time. And so what this plot is just showing is, depending on the kind of category of disk, the amount of mass inferred goes down in time. What does that mean? That means that these disks that form planets go away in time. They dissipate. And so there's only a limited amount of time during which the planets that are going to form in the disk can form. Because once the disk is gone, you got no more stuff. And exactly how long it takes is probably a few million years. This plot is kind of a classic plot showing what each point here is showing for a given cluster of stars for which we can measure the age, what fraction of those stars are seen to have disks, right? And exactly whether they have disks is inferred from whether they have hot dust, right? And so what you can see is very, very young clusters of stars. Pretty much all of those stars have hot dust, so they pretty much universally have disks. Whereas very old, clusters older than 5 or 10 million years, almost none of the stars have hot dust, so they don't have disks anymore, we don't think. And the typical time frame for this to go down is a few million years. And so people generally kind of wave their hands like I like to do a lot, and they say, well, the typical time frame for the dissipation of disks is therefore a few million years. And that kind of is a constraint. That's a very, very strong constraint on the formation of planets, especially of giant gaseous planets. Because you can imagine, well, maybe the gas disk goes away after a few million years, but the dust and the rock stuff stick around and bash together to form Earth. But if you want to form a gaseous planet like Jupiter, that has to form fast anyway, while the gas is still there. Right? So this is a very strong constraint specifically on the formation of gaseous planets. Just to quickly summarize the observational constraints, there's a lot of diversity of planetary systems. The solar system we are pretty confident is unusual at about the 1% level. Super Earths are all over the place. And, there's a window in which most planets have to form, which is a few million years. This is the lifetime of gaseous planet-forming disks that we see around other stars. So that's the end of observational constraints. Moving on to stages of planet formation. And so we're going to go through many different stages here. Growing from dust to planets, moving around. All right, and so here's a list of the kind of the things we're going to cover in addition to random things that pop up. So kind of the cast of characters that you'll see, we're going to start off with very small dust grains that I didn't include on the plot, that are, micron size or so. Then words that you'll hear over and over again are things like pebbles and planetesimals and planetary embryos or protoplanets sometimes. And so just so you know what we're talking about, pebbles are things that are maybe a millimeter to 10 centimeters in size. So, kind of rocks like pebbles you would find on a beach. Those are the kind of things that we're talking about. Planetesimals are bigger. They're more like, the typical number is more like 100 kilometers in size. So they're big things, right? I always think of them as big potato-shaped things like from Star Wars, but they're big. They're like 100 kilometers in size. Then planetary embryos are things like the moon or Mars. They're big, basically mini planets already. And sometimes when we talk about planetary embryos among rocky planets, we're typically talking about things that are more like moon or Mars. Oftentimes, the word cores for giant planets comes up. And then, since it's still a small version of what's to come, The small version is much bigger, and it's often things that are more like Earth size, okay, but out in the giant planet realm. And I'll try to explain this as we go, but in case not, this is why I'm doing this. So here's the cartoon version of the stages of planet formation, and then we'll get into the details of different steps. So starting from dust grains within, of course, as you can see on the top left, within a gas-dominated disk around a young star. Starting from dust grains, these things can stick together to form, millimeter or slightly bigger sized pebbles. Pebbles don't just stick around, they often drift within the disk. They don't like to stay stationary, they often spiral inward. And they can clump and form planetesimals. Right? As we know, 100-kilometer sized planetesimals. Planetesimals can bash into each other or grab onto other pebbles that are sticking around and grow into planetary embryos or cores. While there's still gas in the disk, those cores also can change their orbits due to orbital migration. And when they're this size object, they're embedded within the disk, they launch these really pretty spiral density waves, and they can migrate around. It's called type 1 migration. While there's still gas in the disk, large enough planetary embryos or cores can also grow into gaseous planets like Jupiter. And those can also migrate, and they can transition to a different type of migration that we usually call type 2, where there's still some pretty density waves, but instead of being embedded within the disk, the planet has basically carved a gap, an annular gap within the disk. Once the gas is gone, after a few million years, like we saw, well, systems of giant planets can go unstable. And this little series of circles is trying to show you that starting from a system with many planets, they can go unstable and kick each other around and end up with just one or two planets with very stretched out orbits, like we'll talk about. And once the gas is gone, there's also kind of like a final phase of giant impacts. Giant impacts can also happen while the gas is around, but we think there may have been a final phase of giant impacts, at least for the solar system. And that's kind of the final sweep up of stuff, the final formation of the rocky terrestrial planets. So this is the cartoon version of where we're going. And we're not going to talk in infinite detail about each of these, but this is kind of the general big picture of what we're talking about. So in terms of a size scale, here's the general size scale of things. So there's a giant variety of, size scales going from tiny little dust up to planets. And so what are the physics of how that happens? Okay? So starting from very small things, like I said, we have observations. We can see dust at small, very small dust. That's a nice thing. We can actually observe it, and we can observe the planets. And as I was introducing early on, planet formation is a lot of what happens in between these two size scales. So on very small size scales, objects actually stick. You don't often think of, if you throw two rocks together, they don't usually stick. But within the context of very slow, collisions within a gas-dominated disk, little pieces of dust have been shown that they actually grow up to a certain size scale. So this kind of diagram just shows the different processes involved in the sticking. There have been some really impressive, detailed laboratory measurements to show the different regimes of how dust sticks, when it sticks, what conditions are required, and exactly how large a body can grow by things bashing into each other. And it's typically pebble size, right? Centimeter-ish size or so is about as far as this process will go before rocks don't grow anymore. They just bounce off, or they even break into small pieces. There's also a size scale. Like I mentioned before, there's a size range where there's rapid inspiraling. Okay? And we'll talk a little bit more about that later. This is a key thing that this will come up repeatedly. So let me just kind of explain it very briefly. The idea is that gas moves around a star at a certain speed, and large objects move at a slightly different speed. Right? The reason for that is that the gas has an extra form of support from radial pressure, from temperature, whereas objects that are just doing gravity don't. And what happens is they feel a headwind. And things that are very small but still feel this headwind, they have very little inertia, and so they spiral in quickly. And the things that spiral in the fastest are pebbles. And so that limits how fast, how big things can grow, because if things spiral too fast, then they can't keep growing. And so there's also there's other barriers to growth. involving the strength regimes, but we won't talk about that. And let's just move on. So a key step in all this is really this transition from very microscopic things that are pebble-sized to things that we think of as macroscopic solar system bodies. And that, the smallest ones of those are planetesimals. So planetesimal formation is kind of a key landmark process in any planet-forming disk. If you're going to form planets, you got to form planetesimals somewhere. And so how does this work? Here's a very simplified version of how this works. And so the idea here is kind of, as I was mentioning before, that gas orbits at a certain speed, and the speed at which gas orbits is basically, it's following a gravitational path, but it has an extra pressure support because gas closer to the star is a little hotter, and so it pushes outward a little bit on the next little bit of gas. And so it actually rotates slightly slower than a perfect gravitational Keplerian orbit. And so an object, a particle that's drifting within this gas, feels a headwind because it's going a little bit faster. And what does the headwind do? Because of drag and trying to pile up gas, it slows it down. That loses orbital energy and causes it to spiral inward. Okay? And that causes things to drift. And the typical time scale for things to drift, as you can see, depends on the details. So don't worry about all the different curves exactly, but the drift can be fast. It can be on the time scale of, say, thousands of years or so. And that's a lot faster than the time scale, the lifetime of planet-forming disks. So the drift is a key process we need to take into account because it happens pretty fast. So here's kind of a very simple kind of way of understanding what's the current thinking about how planetesimals form. The current kind of predominant idea is called, the predominant process, I should say, is called the streaming instability. And so the idea is this. Like as we saw before with our particle that's orbiting a star and feeling a drag force, it starts to spiral inward. But it's not alone. Other particles are spiraling inward also. And by chance, other particles can be kind of close together. So what happens when enough particles are close together, then you have a concentration of solids relative to the gas in a local area. That can actually act to speed up the gas a little bit. And it changes this dynamic. Instead of if you have enough of the dust of these particles, then the dust is actually affecting the gas as much as the gas was affecting the dust. And what that can do is it can reduce this kind of in-spiraling effect. And what that does is the neck, basically leaves this clump there and it's not moving very much, so that any other little dust particles that come in can just join the pile. And so you can have this kind of concentration of dust that leads to a further concentration and a further concentration. And in the end, you can end up with a very strong concentration of stuff. Here's a really cool animation of a visualization of the kind of what it looks like, what the streaming instability actually looks like within a model of a planet-forming disk. And so this animation was drawn directly from the highest resolution simulations that are out there now. And so zooming in on this little part of this planet-forming disk, what you can see is this little slice. An actual simulation is usually just a little slice like this. And you can see these kind of waves of dust are clumping together. And in certain regions, that kind of radial clump is going to become dense enough that in certain parts of it, planetesimals can form. And this kind of model, this general picture for how planetesimals form has been shown to be very robust in terms of the dynamics. It also kind of makes some sense in terms of how these things should go, this jump from small to much bigger objects. What's still being worked out is exactly where and when we think this is happening, how it depends on all the disk properties. Where and when did our solar system's first planetesimals form? These are questions that we still don't have the answers to, but that's kind of the current wave of studies about this. And so this plot here is showing kind of the outcome of simulations of the streaming instability. And what it's really showing is just that by analyzing this type of simulation, it looks like objects as large as several hundred kilometers in size can form. right? That's as big as the biggest asteroids, basically. The biggest asteroid series has a radius of about 500 kilometers. So this is up to almost the biggest asteroid. And what's interesting also is they don't tend to form in kind of a random way. There's many different studies have found a relatively similar size distribution. And that's kind of interesting because it compares pretty well with the actual observed size distribution of the asteroids. And so that's not like a nail in the coffin, this is absolutely what happened kind of thing, but it goes in the right direction. It's very encouraging, and it seems like the streaming instability has the potential to explain how planetesimals form. Now, where do planetesimals form is, as I mentioned, a whole different question. And so to get at that, ideally, you need, again, a whole nother layer of complicated computer modeling where there's a disk, and you want to study the evolution of the structure of a gaseous disk, and then look at where the particles are clumping and the streaming instability happens within such a disk. And so here are two plots from different studies of that kind of exercise. So in the one on the left, all of the planetesimals form basically in a ring. And so a lot of mass end up forming, but all the planetesimals are in one small ring centered at about Earth's orbiter. In the one on the right, it's the opposite. There's a broad disk of planetesimals that formed, especially further out. And so, this is something that's currently evolving. There's some new studies. There was a new one that came out just this year, proposing that planetesimals form kind of in this way that sweeps across different parts of the sun, basically of planet-forming disks. This one was focusing on the solar system specifically. And so in their model, planetesimals formed basically in different regions, basically following condensation fronts. Zones where you had the right temperature, that was right where, for example, liquid water could condense into ice. And so I'm only mentioning this as to emphasize that it's kind of a current area of very active study. And it's a key thing because we're pretty confident that planets form from planetesimals, but to really understand when and where they form, we need to know when and where the planetesimals form. And we don't really quite know that yet. So anyhow, this is the story so far. Looking back at our cast of characters, get where pebbles were, planetesimals. Now what happens when pebbles and planetesimals are together at the same time? That's going to lead us to forming even larger things. And that'll lead to a process called pebble accretion. And so here the idea is, in a simple cartoon again, the black dot is a large planetesimal that is formed, and the blue things are pebbles. They're the dust that grew big enough by bashing into each other to drift within the disk because they feel its headwind. And what's interesting is, they can kind of, from the point of view of the planetesimal, this dust can kind of drift inward slowly. And so what happens now? That's the process of pebble accretion. And it turns out that pebble accretion can be very efficient. And so this little animation is showing this large planetesimal, as it's plowing through pebbles, the pebbles are much more likely to kind of spiral in and end up colliding with the large guy than other planetesimals. And the reason for that is the interaction with the gas. It helps the pebbles basically spiral in and do that. And so what this does is it makes it that the large planetesimal can grab onto drifting pebbles very efficiently, much more efficiently than if it was just grabbing onto other smaller planetesimals. And where this matters is especially for the giant planets. We think that this is kind of a key process for how the cores of the giant planets form. And so we'll talk more about the details of that later. But what you can see is this plot is basically showing how long it takes, with some simple assumptions, for a large core, something like the 10 or so Earth mass core of Jupiter to form in different parts of, as a function of the distance from the sun. So there's some, assumptions that go in here, but the key point is that it takes a lot more time to form a core out of planetesimals than it does out of pebbles. And, that we know that disks only last for a few million years, and pebble accretion can explain how big cores form within that time frame, whereas planetesimal accretion cannot. And so this is a key reason that pebble accretion, in addition to kind of connecting the dots in a little bit more of a smooth way, it's why we like pebble accretion as this kind of process that's very important for forming giant planet cores. Another kind of aspect of this that's interesting, and I'm not going to talk about this much, but it's interesting that pebble accretion is actually self-limiting. So it can't just go on and one big planetesimal can't gobble up all the pebbles. And the reason for that is that once it gets big enough, a large growing object, large growing core, actually creates a density wave outside its orbit. And so what this plot is showing is actually the pressure within a disk, and that red part outside the planet's orbit. Basically, that line there is showing what is really a ring around the star. And so it's kind of unstretched out like that. And that outer red streak is a pressure wave exterior to the growing core's orbit that acts to trap pebbles. So this little yellow pebble that I put on cartoon version, it will spiral in and then get trapped in that pressure wave rather than keep going and bash onto the growing core. Right? And so at a given size, typically maybe 20 Earth masses or so at Jupiter's orbit for certain disk assumptions, pebble accretion just shuts itself off. And that's kind of interesting. In some cases, the planetesimal accretion idea, which was very predominant back in the day, is probably still as important. And so we actually still think that in the rocky planet realm, planetary embryos probably do grow, but mostly from planetesimals bashing into each other for various reasons that I won't go into. We still think that there are parts of planetary systems where most of the growth probably does happen from planetesimals bashing into each other in this process of runaway and oligarchic growth, but probably not for the giant planet cores. The next kind of process to talk about is migration. And what this animation shows here is a growing core, how it interacts with the disk. And so the mass of this object is being artificially increased as it orbits. But what you can see is these spiral density waves are getting stronger and stronger as it gets more and more massive, and eventually a gap is carved. Right? And this happens because of gravitational interactions between the planet and a disk. And this leads to orbital migration. And in the low mass regime, this is what I call is often called type 1 migration. The low mass regime is where a planet is still embedded within a disk. And so what happens is basically these growing planets launch spiral density waves within the disk. And so in this image here, this is an image from a hydrodynamical simulation of 5 planets, each of which is about 3 times more massive than Earth. They're all within this one disk. And each of them has launched its own set of spiral density waves. And those spiral density waves they basically induce a torque on the planet's orbit. And the torque changes the planet's orbit. It can cause the planet's orbit to shrink or grow. Usually to shrink, but not always. And a couple kind of key pieces in here are that more massive planets are caused to migrate faster. And this only really matters for planets that are more massive than Mars or Earth or so. It depends really on how much gas is there. But typically for planets less massive than Earth, migration can happen, but it's very slow. And where is this migration happening? Right, it's happening within the disk. And so the study of the physics of what's really going on within gas-dominated planet-forming disks is a very key thing, because this is where all the action is. And so this is a cartoon from a review paper, just kind of trying to illustrate the different processes at work. And you can see there's a lot of different processes going on. There's debates as to which ones dominate in which regions, exactly what's going on. But I'm just including this to kind of illustrate the complexity of what's going on. One kind of key point that I'll mention is that we don't think that the disks go all the way to the central star. They don't touch the star. As gas from the inner parts of the disk kind of moves slowly inward and ends up on the star, it doesn't do so by just bashing into it. As it gets to a certain distance, closer than a given distance, gas is actually funneled along magnetic field lines onto the star. And we'll see later that matters in terms of looking at the migration of planets as they get very close to their stars. We don't think that they can just follow the disk onto the star. We think they get stuck at a given point because these disks have inner edges corresponding to where those magnetic field lines kind of connect to the disk. And here's a slide to illustrate what I just said. In terms of this migration, we think as a planet is migrating, it will basically keep going, but then stop at a given point, simply because there's nothing else to keep pushing it inward. Now, here's kind of a simple kind of cartoon of how these cores fit into the giant planet formation picture. The standard model is called core accretion. And I'm just going to go over this very quickly because we'll talk about it in a little more detail later on in the giant exoplanet part. But still the standard picture of how giant planets form is that a large core of 5 or 10 or 20 Earth masses grows and it grabs onto some gas. That's kind of the standard picture for gas giant planet formation right now. And exactly how that happens is kind of illustrated here. We think it happens, this is basically showing the mass of a planet as a function of time. There's an early phase where a core grows rapidly, and then a longer phase where it piles on gas. That gas has to cool down so that it can compress so that more gas can get piled on. And this process keeps going until a critical point is reached where the kind of shrinking down is balanced by a lot more stuff piling on, and it can become a runaway and a giant planet can form fast. And we'll talk more about that later. And as a gas giant planet forms, then it can transition to this other mode of migration called type 2. In type 2, there's a gap has been carved such that the planet is no longer embedded within the disk, it's rather kind of created a gap. And so then it's the disk's radial evolution that determines how fast the planet will migrate. It basically kind of follows what the disk is doing, more or less. And this is generally much slower. So it's a much slower form of migration. Small planets we think can kind of zip around pretty quickly within the disk, but once they're big, they're anchored to what the disk is doing, which we think is a lot slower. Kind of like, little kids zoom around all over the place and adults just kind of move slowly and say, and mostly this is inward, this form of migration, but there are certain exceptions. There's certain kind of interesting cases where it can actually be outward. And that might matter a lot for specific systems, possibly the solar system via this grand TAC model. Another process that's key is kind of to explain the eccentricity distribution that we talked about. There's a whole other process that we think is key. So we think that the reason that there's a lot of planets close to their stars is because of orbital migration that shrinks the orbits of giant planets. And we think a different process can explain why a lot of giant planets have stretched out eccentric orbits. And the dominant process here is called planet-planet scattering. Dynamical instabilities, planet-planet scattering, they mean the same thing. So what's going on here, we think that when one giant planet forms, probably several can form. And over long time scales, in some systems, the long kicks between planets can change the shape of their orbits and cause two planets' orbits to cross. And that doesn't mean that they're going to collide, at least not for giant planets. In this animation, there was a series of close encounters between the planets. And then at the end, there was a really strong gravitational kick that sent one planet off, never to return. And so that planet got ejected into interstellar space, and the surviving planets, you can see, have a much more stretched out orbits. And so you can think of the planets' stretched out orbits as reminders of their violent past, right? Because these instabilities are very violent from a dynamical point of view. But then kind of the late phases here, what the disks do at the late phases can matter too. And so one kind of key process late in the game is disks evaporate. And so we often talk, like I talked about before, disks go away after a few million years. What does that mean? Well, kind of the predominant thinking is that disks actually evaporate from the inside out. Once they sort of slowly drain away for a while, when they're below a certain critical density, the energetic radiation from the central star can basically give them a strong kick and clear them out from the inside out. And there can be this kind of outward sweeping edge of the disk as it slowly dissipates. And that, can have some consequences actually for planets' orbits. If they are migrating, for example, then some planets can still migrate while others have stopped because there's only gas in certain areas. And kind of the final sweep up after the gas is gone, kind of the final big energetic process of planet formation is this kind of late stage accretion, this final sweep up of leftover planetesimals and embryos after the gas is gone into rocky planets. And that's characterized by big impacts between objects. For example, this is just an artist's impression of the moon forming impact, where two large planets, bashed into each other, where some big thing that was maybe the size of Mars or so bashed into the Earth and created the moon. And these impacts, these giant impacts, are often not quite as smooth as all that. They don't always lead to planetary growth. They can actually erode planets. And so here's a simulation of an actual collision. As you can see, in this case, a slightly off-center collision creates this big shoot-off of ejecta and stuff. There's stuff all over the place. So it's not necessarily a really clean process. There's a lot of these big impacts that are just creating stuff all over the place. And at the end, kind of once the giant impact phase is over, I'm not going to talk much about this, but there's a final, very final sweep-up phase, which continues to this day, which is kind of the late accretion, the kind of final sweep-up of leftover planetesimals onto planets. And what's interesting about this is that it's constrained. We have geochemical measurements that constrain it. And we know, for example, that something like 0.5% of Earth's mass was delivered after the moon forming impact. And some of these very, very late impacts were like the ones that killed the dinosaurs and stuff. So those still happen. They're not usually thought of in that way. But that's kind of the very final phases of planet formation. Basically, this is a quick summary of the stages of planet formation. Remember, we went through planetesimal formation, pebble accretion, and planetesimal accretion in certain cases, migration, type 1, type 2, gas accretion, giant impacts, planet scattering, late accretion. All these things are these are the pieces of the puzzle that we're trying to put together. Just as a very, very final summary of this part, let me just kind of put together in graphic mode, simple, again, cartoon graphic mode, these stages of planet formation. We talked about them individually. Let's look at them together in a slightly more concrete way than I showed before. And so what we're looking at here is on the y-axis, very rough size scale of objects. On the x-axis, a very rough time scale. And we're just going to kind of put the key phases of growth on here to see what they look like. First of all, it's important to take into account that the gas disk only lasts for a few million years. Okay, so it doesn't keep going forever. Maybe 3, maybe 5 million years, something like that. So starting off from small dust grains, micron-sized dust grains, as we saw, they can stick together and grow up to pebble size, up to maybe millimeter or centimeter size. Then those pebbles can drift, they can clump in certain places and grow by the streaming instability into planetesimals. Right? This is a key big jump in size from millimeter, centimeter sized things up to 100-kilometer scale planetesimals. Then planetesimals can continue to grow by bashing into each other, by grabbing onto some pebbles. That process is relatively slow among rocky things where there's not as much stuff inside the snowline. And then later on, once there's a collection of these planetary embryos, they bash into each other. Each of the jumps in this staircase is kind of a giant impact between two growing planetary embryos. There's a final one, which for the Earth would be the moon forming impact, the final embryo impact. And then there's this kind of late veneer, this late accretion, this small tail of sweeping up of the leftover small things of about 0.5% of mass for the Earth. And that's kind of a cartoon version of how we think Earth grew. Something like Jupiter would have grown more or less the same early on, but we think pebble accretion would have been much faster and been much more efficient early on. And so starting from a large planetesimal, Jupiter's core could have grown up to many Earth masses very fast within, I don't know, a million years, something like that. And then after that, it could grab onto gas and grow, by core accretion up into a full gas giant planet. And so this is kind of the different growth track for a planet like Jupiter. And of course, these are not the only possible growth tracks. These are kind of very simple estimates of how we think Jupiter and Earth grew. And of course, on top of this is the idea of migration. And so we, at least in standard picture, Earth and its building blocks probably didn't migrate much, but Jupiter's core probably did. It probably could not have avoided migrating a lot. And so exactly how that plays into the game is something we'll talk about a little later. But anyhow, this is kind of a recap of the key pieces of planet formation and how they sort of fit together for two examples. And we'll look in more detail at how these pieces can fit together for more concrete examples for populations of planets and for our own solar system.